Okay, so we are going to discuss this next experiment, which is the electrical conductivity of aqueous solutions experiment. And the goal here is to observe that certain solutions conduct electricity and certain solutions don't. And then using the definition of electrolyte solutions, define whether the solution you observe is strong or weak. And then using that information to write the appropriate chemical species that exist in solution. What we want to start with is just talking about what electricity is. It's just a form of energy that we observe because of a flow of charged particles, and typically in this case it will be electrons. The electrons have to be able to go from one place to another through what we call a conductor. The reason that the electrons will flow is because there are two different points in space where there is a potential difference, meaning that one side has more positive and the other side has more negative. Now, because electrons are negatively charged, and electrostatic law describes that like charges will repel and opposite charges will attract, the electrons will travel from the side with more negative charge to the side with more positive charge. That flow has to occur through a conductor, which could be a wire, and the flow is going to occur until the two sides are equally balanced in charge. You've seen that solid metals is typically used for this purpose as a conductor, for example, copper wire. That works because metals contain free electrons in their atoms. Those are just randomly distributed in space, as shown in this picture right here. This is a metal sample with all its atoms and all its electrons. If you put this in a potential difference, then one side is going to have a negative and the other side is going to have a positive. So now there is a push for all those electrons to flow in that direction. It's exactly what this thing looks like here. So when all of the electrons are flowing towards that direction, that's what we call electricity. We can see this pretty clearly in this example. Here we have a battery where one side of the battery is positive and the other side of the battery is negative. Now the battery is connected in this circuit where the negative side is connected through a small light bulb, and then this then is connected through a piece of sodium metal, and then the other side is also connected to that same piece of sodium metal, thereby forming a circuit. Now, if you don't have the sodium metal and these two pieces of nail is just held in air, this light bulb will not turn on. However, when you push both nail into the sodium metal, you see the light bulb turn on. And the reason is because now the electron can flow. Again, this is the negative end, so it gets pushed through and then going into the positive end of the battery. Now, it turns out that ions can also conduct electricity, but they have to be able to move. So ions that are fixed in place can't conduct electricity. And the reason that the mobile ions can conduct electricity is because the electrons hop onto the ions and the ions move from the negative side to the positive side, and that's what allowing the electricity to flow. The more mobile ions you have, the stronger the electrical conductivity of a sample. Whereas if you just have a small number of these mobile ions, and you only see weak conductivity of the electricity. So same setup right here. So if there's a lot of ions in the solution, you're going to see a really bright light bulb. When there are only a few ions, you'll see a weaker light bulb. And then when there's no ions, you'll have no light at all. And these are what we call strong, weak, and non-electrolyte solutions. So we can figure out in terms of chemical species what are strong, weak, and non-electrolytes. So strong electrolytes are all the soluble salts, all the strong acids, and all the strong bases. Weak electrolytes, on the other hand, are all the insoluble salts, which just means that they're salt that only dissolve very, very little into the solution, weak acids and weak bases. Non-electrolytes are solutions that don't conduct electricity, so they can't be any type of ionic compounds or species that produce ions, so they have to be covalent compounds that are not acid or base. These have to dissolve in water, so they have to be polar covalent compounds. Now, the experiment that you'll do today would be very similar to this picture right here. You will have a light bulb or some type of instrument that's connected to wires. The wires can then be submerged into different solutions, and then you'll see whether that light bulb turns on brightly, dimly, or not at all, and that would be the case for strong, weak, and non-electrolyte. Microscopically, if you can see into the solution, you'll see that the strong electrolyte has a lot of ions. The weak electrolyte only has a couple of ions, with most of the species still bonded together. And then the non-electrolytes will have no ions at all, with all the species bonded together in their molecular form. It's important that we understand how solutions conduct electricity, because we have to write the chemical equation differently when we're dealing with strong electrolytes versus weak or non-electrolyte solutions. So here's a quick example. We have three different solutions. One is a strong electrolyte, AB. The other one is a weak electrolyte called CD. And then the last one is a non-electrolyte called EF. If you dissolve them in water, first off, all of them in their molecular form would be written as shown on the left here, which is ABAQ, CDAQ, and EFAQ. However, the correct form that you have to write based on what we observe would be A plus AQ plus B minus AQ, showing that that strong electrolyte has completely dissociated into its constituent ions. That's why we see a really bright light. The CDAQ, this is the part that's a little hard to write, because in reality, the CD would produce very few ions if it's a weak electrolyte. So you would theoretically want to show those ions, but because you can only write one form, we would write the majority form, which in this case would just be the CD compound in aqueous form. Now, is that 100% correct? Not quite, but we know that the majority of the species exists as the molecular form, as shown right here, with only a couple of these forming ions. And then, of course, with the non-electrolyte, it's pretty easy. We know there's no ions at all, so we just write the dissolved form as EFAQ.